Hey everyone, we are getting down to the last section of the chapter here, and this is going to take place over 2 days, so this is going to be the first video of 2 for section 7.5. And really a lot of what we're doing today is going to be similar to what we've been already doing. We're going to be using proportions to solve for measures of sides in right triangles, but today we're just using these in more kind of word problems or application problems. So that's really the biggest difference. And so a piece of this is going to be knowing how to draw a picture to represent a problem so then you can use proportions appropriately to solve the problem. So we're going to be working with something today called indirect measurement. And all this means is really indirect measurement is allowing us to find distance that cannot be measured directly. So in order, I can't just go out and lay down a tape measure and measure that distance directly. We need another way to do it. An indirect measurement is going to use similar triangles and proportions to measure an object. Okay, so that'll be kind of piece one of this is indirect measurement, and then we're going to be working with scale drawings. And we actually talked a lot about this in section 7.1, so we'll just be kind of revisiting this today. Okay, and again, a scale drawing just represents an object as smaller or larger than its actual size. So for example, like a blueprint of a house. Okay, so the drawing scale is the ratio of any length in the drawing to the corresponding actual length. And really, in 7.1 we talked a lot about this, but instead of calling it the scale, we were really referring to this as the similarity ratio, because it's just the ratio of corresponding sides. So for example, on a map with a scale of 1 centimeter to 1,500 meters, 1 centimeter on the map represents 1,500 meters in actual distance. And again, we've all seen these kind of scales on maps before. Now, for a quick review in terms of measurement, because this will come up a little bit in this chapter, important to remember that centimeters are broken down into millimeters. Right? So I know that 1 centimeter is equal to 10 millimeters. Okay? Then 1 meter is equal to 100 centimeters. And so actually centimeters are pretty easy to work with because centimeters and meters, because meters are based on 100, it's a pretty easy unit to work with. We have to do a little more work when we're measuring in inches and feet, because inches are broken down into 16ths. So it's not quite so nice like centimeters are broken down into tenths. Here we have 16ths. And then we know 1 foot equals 12 inches. And we'll be using that quite a bit in this section. So quickly, we want to do just some quick exercises here with being able to convert back and forth between inches and feet. So my first question says to convert 6 feet and 3 inches into inches. So the first thing I'm going to do is I'm going to take the 6 feet, right? And I know that if I have 6 feet, I'm going to multiply by 12 to get the number of inches, right? And you can think about when we did unit analysis, or not in this class, but when you've done it, we start with 6 feet, and we want to multiply that by something so that our feet cancel. So what I know is that 1 foot is equal to 12 inches. And so that's why up top I'm multiplying 6 by 12. So if I go ahead and do that, I'm going to get 72. So now I know 6 feet is 72 inches, so I'm going to add the 3 inches. So 72 plus 3 is 75 inches. So 6 feet, 3 inches is actually 75 inches. Now, on the other hand, here I want to go from 80 inches, and I want to turn that into feet. But again, here's where we have to be a little careful. So if I start off, I know that 80 inches, well, there's 12 inches per foot, so I'm going to divide by 12. Now, when I do that, if I get my calculator and I take 80 divided by 12, is we get 6.6 repeating. Now, I don't like that calling that 6.6 feet because really feet aren't in tenths. We don't break that down into tenths. So here's what we're going to do. We know the whole number. We're going to take this whole number part. And so I know I've got 6 feet, and then I've got some inches left over. So I know that 6 feet would make up 72 inches. Since I have 80, I have 8 inches left over, so it's going to give me 6 feet and 8 inches. So in the problems we'll be doing today, we'll be going back and forth between feet and inches. So I want to make sure we are all kind of clear on that. If there's any questions, we can go over some more examples tomorrow in class. But for now, we'll go through the examples and we'll kind of deal with those type of situations as they come up. Okay, so here we go. So our goals for today, we're going to be using similar triangles and proportions to solve indirect measurement problems. Okay, we're going to solve for actual distances and lengths given a scale drawing and a scale. And then kind of taking the opposite of that, calculating the dimensions of a scale drawing if I have the scale and the actual measurement. So here's our first example. So the student wanted to find the height of a statue of a pineapple in Australia. And I actually found a picture online. It does exist. Okay, she measured the pineapple shadow and her own shadow. So here's where I'm going to kind of draw a little picture. And again, I'm not going to worry, I'm not an artist here, but I'm just trying to get an idea of what's happening. So we know we're using right triangles. So here's my shadow, right, along the ground here. And we've got a right triangle. And then we've got our really tall pineapple. Kind of looks like one maybe. Okay, there's our lovely pineapple statue. And it has a shadow as well. Okay, so again, we've got another right angle. And really, this shadow is kind of, or the shadow here, this is going to represent the rays of the sun. Those are coming in at congruent angles. So we know we have similar triangles by angle, angle. And so that's why we're able to use similar triangles here. So now we know we've got our person and her shadow and our pineapple. And so let's see what we know. We know that the student's shadow is 2 feet long. So I'm going to mark that there. It says at the same time, the pineapple's shadow measured 8 feet and 9 inches. And says the student's height is 5 feet 4 inches. And we want to know the height of the pineapple in feet. So I'm going to call that x. So now we know we have similar triangles, so we're going to use our proportions. But here's where we have to be careful. If I know the student is 5 inches and 4 feet, or excuse me, 5 feet and 4 inches, I cannot call that 5.4 feet. Those things don't mean the same. So the first thing I'm going to do is convert everything here to inches. So my 2 feet, I know there's, 12 inches in a foot, so this is going to be 24 inches. Here, I know 5 times 12 is 60, plus 4 more inches is going to give me 64 inches. Down here, 8 times 12, let's see, that is going to give me 96 inches, plus I'm going to add 9 more, so I get 105 inches. All right, so now everything's in inches, so now I can set up my proportion. So I know that the height of the person over the height of that pineapple has to be in the same ratio as the leg, the shadow here, to the shadow of the pineapple. So now we're just going to cross multiply and go ahead and solve. So I have 64 times 105. It's going to give me 6,720, and that's going to be equal to 24x. So if I divide by 24 on both sides, I'm going to get x is equal to 280 inches. So now I know the height of that pineapple in inches, but it asked for the height in feet. So here's what I'm going to do. I'm going to take that 280 and I'm going to divide by 12. So I know I have a whole 23 feet. I'm going to use that to represent feet. Now, 23 times 12 is going to give me 276 inches, which means I have 4 inches left over. So I can use this notation, or I can say 23 feet and 4 inches. Both of those are going to mean the same thing. So again, really the only new piece is working a little bit with those unit conversions, but mostly just being able to draw the picture so that you can set up those right triangle relationships. Okay, so that'll be one type of problem that you're going to see over and over again, using shadows to do that indirect measurement. Here's another type we'll see. So it says to find the height of a palm tree, Jasmine placed a mirror on the ground 2.5 meters from its base. So let's see. I've got a big old palm tree here. Oh boy, it's a pretty rough looking palm tree, but we get the idea. Okay, so now she's putting a little mirror here. This is 2.5 meters from its base. And then she stepped back 1.5 meters so that she could see the top of the palm tree in the mirror. So kind of here's what we have. And she's standing here. So if she looks into that mirror, she can see the top of the palm tree. That is a terrible drawing, but that's okay. Let's see. So that's our setup here. It says Jasmine's eyes are approximately 1.9 meters off the ground. And it wants to know what is the height of the palm tree to the nearest tenth of a meter. So now here with meters, it's really nice and easy. We don't have to worry about converting anything because tenths of a meter makes sense here. So let's see. The idea here, if we're thinking about, well, how are these triangles similar? I know these are going to both be right angles. Now, there's a principle said that the light coming into the mirror, the angle that it hits the mirror is the same angle that it's reflected off of that mirror. So really what we have are these two congruent angles here. So again, we're basing this off of angle-angle similarity. So again, once we've got our setup, we're just setting up a proportion. So the height of this person, the ratio of the height of the person to the height of the palm tree has to be in the same ratio as the length of this leg to the length of this leg. And again, we're going to cross multiply. So it's 4.75. And if we divide, we get approximately 3.2 meters. And again, I was careful here. It asked for the tenth of the meter, so I rounded it to the tenth. Okay, so again, you'll see that a lot of type of that mirror problem as we go through the practice as well. All right, let's flip to the next page. We've got two more examples. All right, so now we've got a person standing here, and they measured the distance from point A to one end of the lake, and then measured the distance from point A to the other end of the lake. So now we know these are perpendicular here. So what we're seeing here really is we have two overlapping, let's try that again. Two overlapping triangles. The small one, which is ADB, and then we have the large triangle, which is ACE. And so I know I have these are right angles. And now, again, using that reflexive property that we've used throughout the chapter, I know that A is congruent to angle A. So this turns out to be another example of angle-angle similarity. And so what I'm trying to find is this distance D here in the picture across the lake. So I'm going to transfer what I know here. I know this BD is 40. I know AB is 320. And then AC, I'm actually going to add the 320 plus 162, and I get 482. So now we're going to set up our proportions again. I know that the ratio of 320 to 482 has to be the same as the ratio of 40 to that D, the distance across the lake. So we'll cross multiply. 320D equals 482 times 40, which is 19,280. I'm going to divide that by 320, and I get, let's see, it says the nearest tenth of a meter, so it'd be about 60.3 meters. Okay, so those are the three types of indirect measurement problems that you might come across in our practice. There'll be slight variations on what you're trying to find, but that's really the idea behind the basic setup for those problems. So the last one we're going to look at here is a quick scale problem. And again, we're not going to do too many of these because you really saw this in section 7.1. So here it says the base of the Lincoln Memorial in Washington, D.C. is approximately 57 meters long and 36 meters wide. So basically that base is just a rectangular shape. So I have 57 meters and 36 meters. And it wants us to calculate the dimensions of a scale drawing of the base of the building that has a scale of 1 centimeter to 15 meters. So I can think of my scale model. Here's my length and my width. Now I know, let's start with the length. So I know the ratio of the length of the model to the actual has to be the same ratio that I'm using in my scale drawing, 1 centimeter to 15 meters. And you'll notice both of my units, since this is the model on top, my units will be centimeters, matches with my 1 centimeter in my ratio. The actual is on the bottom, those units are meters, and in my ratio, if I put it here, those units are meters as well. So now I can just cross multiply. 15x equals 57. And if I divide, I get x equals 3.8. And again, because I'm coming up with the dimensions of the scale drawing, I know my units are going to be centimeters. Now I just do the same thing for the width. So I have the ratio of y, the ratio of the width of my model to the actual building has to be in the same ratio as my scale factor. So now I have 15y equals 36. So 36 divided by 15, I get y equals 2.4 centimeters. So for my model, it's going to be 3.8 centimeters long and 2.4 centimeters wide. Again, not a whole lot new since you had looked at these in 7.1. Just now we're calling that the scale. Oops, I'm sorry, you can't see that. I'm calling it the scale instead of the similarity ratio. All right, so we've got some practice left to do with this, and then we have one section left before the end of this chapter.